My name is Daniel Nenny, and I'm the founder of SemiWiki.com, the open forum for semiconductor professionals. Since going online in 2011, SemiWiki.com has experienced more than 3 million users. If you're not a member of the SemiWiki community, please register as my guest. I hope to see you there. Today's webinar is titled Maximum Performance Using FPGAs with PCIe Gen5 Interfaces. In this webinar, you'll see why you need not only high-speed connectivity, but also the ability to process the incoming data at high speeds to accelerate application performance. You'll learn how to maximize bandwidth using FPGAs that include high-speed PCIe Gen5 interfaces, high-speed network on chip, high-performance GDDR6 memory interfaces, and machine learning processors optimized for AI and ML workloads. We will also highlight several application use cases for PCIe Gen5 enabled FPGAs and highlight important FPGA design considerations to ensure maximum efficiency and bandwidth. The presenter today is Kent Orthner. Kent has worked in the IP, semiconductor, and embedded industry for over 20 years with a focus on all aspects of interconnect, IP interoperability, and FPGA design. At Achronix, Kent contributes to leading-edge FPGA architecture and SoC integration. Please submit your questions or comments in the questions box, and we will respond to them via email after the webinar. Okay, let's get started. Over to you, Kent.
Dan, thank you very much for the introduction. And everyone, thank you for joining me here today as we talk about using FPGAs with PCI Express Gen 5 interfaces. Without further ado, let's get started. So what's new about PCIe Gen 5? So Generation 5 has been designed to enable higher bandwidth applications. As you can see from the table here, when you're looking at a by16 interface, PCI Express Gen 5 now supports up to 128 gigabytes per second of bidirectional throughput. That's a terabit per second of throughput going back and forth between your host PC and your high-performance FPGA. PCI Express Gen 5 also supports more embedded signal integrity technology features, and it's designed to be the technical cornerstone of additional interconnects. If you look at specifications like CXL and NVMe, they're built on top of PCI Express to maximize interoperability. PCI Express Gen 5 will continue to be backwards compatible with previous generations of PCI Express, and this allows us to expect wide deployment in data center and networking applications. Key applications for PCI Express Gen 5 include compute acceleration, which is using some sort of hardware accelerator to help the processor get more work done in a small amount of time. If you look at the trends for artificial intelligence and machine learning, the demands on compute performance are increasing exponentially. Some applications like autonomous vehicles are generating up to 4 terabytes of data per day. And the training models that we're seeing for artificial intelligence implications double in size every 3 to 4 months. As we all know, enterprise workloads are moving more and more to the cloud, accelerated by increasing number of workers from home, and CPUs simply can't keep up. We need heterogeneous compute, which means that we have specialized acceleration hardware to help the CPUs process these enormous loads that are being asked of them. Another application that we're going to look at today is a smart NIC. So a NIC is a network interface card. A smart NIC is one that offloads processing tasks from the CPU so that the CPU is able to spend all of its time doing the processing that's executing the algorithms that are the reason for it to be there in the first place. The smart NIC then takes on a variety of different functions, including any combination of encryption and decryption, firewall, offloading the TCP/IP stack processing, implementing software-defined networking functionality, etc. The third application that we'll look at today is storage acceleration. So this is when your CPU is saving and retrieving data to non-volatile memory, such as hard drives or solid-state drives. So storage acceleration involves using specialized hardware to reduce the CPU load and to improve throughput and latency to your non-volatile storage devices, such as hard drive arrays and flash. So examples of this are inline compression and decompression as you're going to and from your permanent storage, encryption and hashing, erasure coding, deduplication, string and image search, and database operations, such as the ability to sort records, join records together, and do filtering when you're reading records from a database. FPGAs are commonly used in compute acceleration. Looking at the first application, FPGAs are commonly used for compute acceleration. The compute capabilities of modern data centers are crucial to solving some of the world's most critical challenges, including machine learning, video transcoding, and data analytics. If you have an FPGA with PCI Express Gen 5, this allows you to offload the CPU to meet some of these performance requirements. Modern FPGAs can deliver a bidirectional bandwidth of a terabit per second using the by16 mode, and they support the really key requirements of programmability and flexibility. FPGAs provide you with much more flexibility and therefore a better time to market than traditional ASIC accelerators. And a key here, they provide reprogrammable hardware acceleration. Modern FPGAs can deliver high-speed memory access. For example, with the Acronic Speedster 7T1500, we can provide more than 4 terabits per second of GDDR6 memory bandwidth. We can provide high-speed network connectivity, including multiple 400 gigabit per second Ethernet interfaces. And we have excellent cost and power efficiency, especially when compared to CPUs and SoCs that are executing instructions one at a time. For the second application, SmartNIC acceleration, we're seeing again the shift to the cloud and ever more sophisticated AI and ML applications, and we're seeing more and more high-speed networking protocols. A PCI Express Gen 5 enabled FPGA provides high-speed connectivity between your networking subsystem and the CPU, and it allows this shift to higher speed networks and more interfaces. And PCI Express Gen 5, with its 512 gigabits per second of throughput in each direction, is very well matched to a 400 gigabit per second Ethernet link. So FPGA accelerators can handle networking functions, freeing the CPU. To do this, you need high-speed memory and Ethernet interfaces, and you have the ability to reprogram the FPGA hardware accelerator based upon demand. So one moment you might be doing compression, then you reprogram the FPGA to do some deep packet inspection. As the workload changes, you might end up offloading some of your software-defined networking functionality. Having an FPGA there allows you to adapt to new algorithms or protocols without having to redesign the hardware and have a new tape out of your ASIC. So with modern FPGAs, the challenge that we have as an FPGA provider is how do we deliver this fire hose of data to the FPGA computational elements? And what we're going to do today is map these 3 applications to a modern FPGA that has an on-chip network that's specifically architected to alleviate these bandwidth challenges. So the third application, again, is the storage acceleration. So the common thread here is programmability and flexibility to deal with the new algorithms and changing standards. FPGAs are ideal for these acceleration applications. So a common protocol here is for non-volatile storage is non-volatile memory express, called NVMe. This is something that's built on top of PCI Express. The PCIe bus offers several high-speed lanes that can be used in parallel, and NVMe has almost completely displaced SCSI, which was the protocol of choice in the past. There's a couple of different modes of operation when you're looking at FPGA-based storage acceleration. So the first one here that I'm showing is called local storage acceleration. So here you need an FPGA that has multiple PCI Express Gen 5 interfaces. One's connected on the north side here to the host, and the other one is connected on the south side, supporting NVMe to connect to the storage device interface. Another flavor of this is remote storage application. Here the connectivity between the FPGA and the host is identical, but instead of connecting to a local storage array over NVMe, you would use a remote DMA transfer protocol such as RoCE, which is RDMA over Converged Ethernet, to talk to a storage array that might be further away. A third model is called computational storage. This is relatively new. The idea here is to move the compute acceleration to be close to the storage array itself. This increases algorithmic performance because it's really close to the storage array, and it reduces network trafficking. So for example, if you're reading from a database and you're filtering a bunch of records, you can filter the records before providing the response over the network, so you don't have the entire data set traversing the network, you only have the filtered response. So here we use Ethernet to accept the remote DMA transactions over RoCE from the host, and then we use a PCI interface to support NVMe locally to the storage array. So in today's presentation, we're going to focus on the data flows that flow through the FPGA, and these you'll note are common to all 3 applications. So the question here is, how do we get this data between PCI Express, Ethernet, the external memory, and then the acceleration units that we have in the FPGA core? I'm showing here some examples of acceleration units. The functionality of the acceleration units doesn't matter so much. We're focusing on the data flow. So first of all, we'll look at PCI Express. In a traditional FPGA, the PCI Express core is adjacent to the FPGA, and to communicate with external memory, the PCI Express data travels across the FPGA to get to the external memory. Memory coming from Ethernet, likewise, abuts the FPGA core and is distributed by the FPGA to the external memory. On the way back, some logic inside the FPGA core needs to read from memory and then push it to the boundary of the FPGA that's next to the Ethernet core. On top of that, we have the PCI Express traffic that's coming into the accelerators. And at the point where we have the Ethernet receive and the Ethernet transmit logic, we're connecting that up to the accelerators as well. And then finally, the accelerator blocks themselves need to be able to get to these external memory interfaces to get the data that they need to perform the operations in question. So you can see here that this FPGA logic is getting pretty busy, and we end up with hotspots and congestion spread all over the place. So when we're looking at these very wide interfaces that are running at very high speeds, in FPGAs, it can be difficult to meet timing with these interfaces at the best of time. Once you add all of this congestion right at the point where the FPGA logic touches the external interfaces, that makes it much more difficult. A traditional approach to this is to add pipelining, but this significantly increases logic area when you're talking about buses that are 500 or 1,000 bits wide. So the solution that we have is a high bandwidth network on chip that runs through the core of the FPGA. So you can see all of these links here running horizontally and vertical inside the FPGA core. Each one of this provides 256 bits of data plus control running at 2 gigahertz. So this gives us a total of 512 gigabits per second on every one of these links. At each intersection, we both have a master network access point and a slave network access point. And each one of these can be configured as either a memory mapped or a streaming protocol. We have 8 rows by 10 columns. That gives us 80 intersections, which is 160 network access points. So by using this on-chip network, this provides you with guaranteed high-performance connectivity inside the FPGA core. This is high throughput and low latency, and also gives you direct connection to all of these external interfaces. It runs at 2 gig, which means that it's decoupled from the logic inside the FPGA, and we take care of all of the clock domain crossing for you. This makes designs much, much easier because this network works directly out of the box. You can connect your logic and drive it with AXI streaming or packetized interfaces. And this means that you don't have congestion around the edge of the chip. We can deliver the data to you wherever your logic resides in the core, which significantly eases time enclosure and eliminates floor planning challenges that you have in traditional FPGAs. So with that, let's look at the specific data flows that we just looked at, but now in the context of a FPGA that uses the NOC. One of the things that I'll point out here is because of the technology that we're using to deliver the Ethernet traffic, you no longer need to run your Ethernet interface at 724 megahertz to be able to deliver 400 gigabits per second of Ethernet traffic. We've been able to reduce this to only 506, and I'll talk about how we do that in a few slides. So first of all, we talked about the PCI Express core being able to talk to memory. So instead of the PCI Express data going into the FPGA core and the FPGA core delivering it, our network takes care of that for you. All the PCIe core needs to do is issue a write command or a read command with the appropriate address, and it's delivered to the appropriate memory interface with no FPGA logic whatsoever. You don't have to write a single line of Verilog code. For incoming Ethernet traffic, we deliver it down the column to your logic. You can have your receive block, your transmit block, and then your bits of logic are able to issue read and write transactions onto our network in order to access any piece of external memory in the entire system. So the only logic that you've written here is a small receive control block that takes the packets and writes it to memory, or that reads from memory and issues that back to the column that sends it out to the Ethernet link. PCI Express has the ability to talk to the various accelerators that are inside the core by issuing transactions that have appropriate addresses. Every slave network access point that I showed in the previous picture has a unique address in the system, and by using that address, PCI Express is able to send commands directly to have them delivered exactly to the location on the device where they're required. Likewise, the various encryption blocks are able to receive and transmit Ethernet traffic using these yellow links here on the network. So this receive block, for example, could indicate that a given packet, instead of going to memory, is to go to the compression block. And then that traffic can be carried horizontally and vertical on the different segments of the network to be delivered using a minimum of FPGA resources. For the accelerator blocks themselves to talk to memory, they can again use a local network access point to issue transactions that bring them across these green links to the most convenient or the most appropriate segment of external memory. One of the nice things about this network implementation is that every single location inside the FPGA core is able to access every single location of external memory without having to be physically positioned close to it. So you might wonder about NOC congestion. Haven't we just moved the problem of FPGA congestion to be NOC congestion instead? Well, when we designed this, we looked very carefully at every single link in the NOC, and we thought about what's the worst case traffic that can be traveling across it, and then we sized it appropriately. So that means that for common traffic patterns, you're going to run out of memory bandwidth before you run out of NOC bandwidth. So as an example, this segment right here is able to saturate all of the GDDR interfaces here in the northwest corner with data coming from the NOC, and at the same time carry PCI Express traffic down here to the southwest, all without running out of bandwidth. So let's go back to our three applications. So let's first look at the compute acceleration. Here, let's think about machine learning inference. The host needs to be able to take advantage of this array of similar compute engines that have access to high-speed external memory. It needs to fill the memory, provide data to the compute engines, and then collect the result of the computation. So how does this work? First of all, the host can populate all of the external memory without using the FPGA whatsoever. At runtime, data arrives from the host. It can be sent to all of the different compute nodes, again, without using any FPGA logic. Each compute node can either read its data from the host by issuing read transactions to the PCI Express core, or it can be written to by the host where the host is in control of the situation and it's issuing transactions to the compute nodes. Or we can use the DMA engine that's built into the PCI Express core and it takes care of all of the data transfers. While the compute nodes are doing their work, they're all able to read and write the external memory by issuing commands to their local network access points. And even though they're all issuing commands at the same time, possibly to the same network interfaces, our NOC takes care of all of the arbitration and ensures that the responses are provided in the correct order. Compute blocks can also communicate with each other. It's possible for a node here to issue a read or write transaction to a node over here. It's also possible to implement a low latency, high throughput streaming connection horizontally in a row or vertically in a column. And of course, it's an FPGA, so the blocks can communicate using the traditional FPGA fabric. Lastly, these compute nodes need to provide a response to the host. In this picture, I'm assuming that one of the compute nodes is responsible for collecting the results from everything else and aggregating them, and it's simply writing to the PCI Express base address to have that communicated back to the host. In a different implementation, you could have all of these compute nodes returning their data to their host independently. So one of the things that we're taking advantage of in this application is the VRAM and machine language processor that we have built into the 17-1500 FPGA. So for each one of these blocks, and we have more than 5,000 of them in the device, we have up to 32 multipliers. We have the ability for driving variable precision, adding and accumulating. We have a floating point multiply accumulate block, an integer multiply accumulate block. And we have a feature called block floating point, which allows you to take advantage of the best of both traditional floating point and integer operations. One of the new innovations that we have is we have tightly coupled this to the BRAM and LRAM register files. This means that you have the ability to read operands from this local memory into the arithmetic units, again, without using any FPGA logic at all. This gives you very high speed operation very efficiently. And we can also cascade these blocks vertically inside a column so that you can have very deep or very wide memories, and they can take advantage of very deep multiply accumulate chains without using any FPGA routing or FPGA resources. Okay, if we get back to the NOC, we have local to every single network access point an address translation table. The idea here is that you can have different compute nodes that are all addressing the same memory, in this case location 0, they're both accessing location 0, but the address translation table is translating that address so that they're actually seeing different locations in memory here. You can see here that the blue address has been changed from 00 to 10, which means that this is accessing GDDR6 interface 1 page 0. So you've only implemented your RTL for your compute engine once. it only has to worry about one address for its local memory, but at the system level, it's remapped so that both compute engines' local memory are kept unique. This also allows for better security. You can configure the address translation table to prevent certain accelerators from seeing portions of the address space. So in this case, if compute engine number 1 tries to access address 2000, the address translation table blocks the transaction and provides an appropriate error response. We have another feature that we've built in to enable this kind of very high performance interface. So in order to offload a host as much as possible, you want to minimize the number of DMA transactions the host has to take care of. That means that you want to be able to transfer contiguous memory spaces to the FPGA accelerator. But to do this, you would need the memory interfaces to be able to keep up with the 512 gigabit per second of unidirectional bandwidth that you're getting from the PCI Express interface. With today's technology, each GDDR6 interface is able to have 256 gigabit per second of unidirectional throughput. So there's not enough throughput here. What we have done is implemented hardware interleaving of the address space for you. So from the host's point of view, it's issuing a single DMA transaction that's transferring a single contiguous block of memory to the FPGA. But the hardware interleaving block that we have here divides this into multiple data streams that are spread across multiple GDDR6 interfaces. This way, we're able to accept the complete 512 gigabit per second of bandwidth into the FPGA and the associated external memory interfaces. So I have here a real world design where we have done exactly what I've been discussing. So we have taken a device and filled it with 2D convolution engines. We're using 94% of the multipliers and the memories in the design. Everything is running at 750 megahertz, and we have not spent any time doing manual placement of logic. Our compilation tools have recognized that each accelerator is centered around a network access point, and what it has done is been able to quite easily, without having to battle congestion, made each one of these blocks independently meet timing. So the timing enclosure here was pretty straightforward. The 512 gigabit per second links going through the network have taken care of the heavy duty traffic. And it was a simple design for users to take care of because they were able to do the block once and just stamp it down. The resulting design is very high performance. We have 38,500 multiplies in every clock cycle, operating at 750 megahertz, giving an effective processing rate of more than 57.5 tera floating point operations per second. Okay, let's move to our second application. Here, let's look at the SmartNIC. So the design goals for this FPGA accelerator are to accept Ethernet traffic from one or more Ethernet MACs, where we have up to 400 gigabits per second per MAC, parse and process this traffic as it comes in, which might include applying a security policy, decrypting, implementing a firewall, routing the traffic to a different egress port, taking care of the TCP/IP offload, and possibly doing key packet inspection. Because this is a SmartNIC, some of the received packets are going to go up to the host via the PCI Express interface. Some of them might go to another MAC based on a switch that's effectively implemented inside the SmartNIC itself. And then we also need to be able to handle PCI Express traffic from the host that's going to go out of an Ethernet switch. So let's take a look at these data flows. So before we look at the specific flow inside of the FPGA, I want to talk to you about an innovation that we have in the 7T1500 called packet mode. When the data arrives from the MAC, it's very, very wide. So for 400 gigabit per second, this is presented from the MAC as a data path that's 1,000 bits wide. And in order to keep up with the throughput, the start of packet can arrive on any of 4 locations and the end of packet can arrive on any of 4 locations. So you can see here that you might get a start of packet on the first clock cycle, and then on the second clock cycle, an end of packet with a start of packet for the next packet. If we simply hand this off to the FPGA, it becomes very difficult for the FPGA to deal with. So what we've done is implemented a hardware algorithm that rearranges this data in time and space to make the job much easier for the FPGA developer and to make the required frequencies easier to meet. So you can see here, we're taking this first packet and we're delivering it in its entirety to a single NAP that has a 256-bit interface. So instead of saying you have to deal with 1,000 bits arriving, We've reduced it to be only 256 bits, and it's instead spread across multiple clock domains. We then take the second packet, deliver it to the second network interface, the third one to the third, the fourth to the fourth, and so on. When we get to the fifth packet, we deliver it to the network interface that's the least busy. And this allows us to efficiently present the data to you using less wasted data spaces in the pipeline and allowing the resulting frequency to be lower. So this significantly simplifies your design. The hardware distributes the packets for you. We can receive packets independently at these 4 locations. And we use some load balancing hardware to send the packets to the least busy network interface. We send sequence numbers with each packet so that even though we're delivering it out of order, you're easily able to rearrange them to be in the correct order if your application even requires that. And because of this packing of data, we now require only 506 megahertz to handle the absolute worst case 400 gigabit per second Ethernet traffic, which includes the worst case interpacket cap, the standard preamble, and the worst case packet size. The hardware that we've implemented will gracefully implement flow control without any support from the packet processing pipelines. And we've implemented such that it works with jumbo packets in excess of 9 kilobytes per packet. For packets that are larger, we have another mode we call the quad segment interface mode, and that's also supported for traditional designs. So how does data flow through our FPGA in this case? So as the data arrives from the Ethernet interface, it's delivered down the column to the receive blocks that you can implement in the FPGA, and then you control where to write that data to memory. If you have decrypting to do, instead of writing the data to memory, you can forward it back down the column. So the data arrives, you look at the header, you push it right back into the column, and the NOC carries it to perhaps a decrypt block. Now, I've shown the decrypt blocks here as being close to the receive blocks. Really, they can be anywhere in the FPGA, and you have control over how the data is routed. Once it's in the external memory, all the host needs to do now is read that external memory to collect the data. There's no need for the FPGA to be involved in actually carrying the data to the PCI Express interface. The receive blocks write to the PCI Express interface to tell the host what's going on, and then the host is able to read the data. When it's time to send data, the receive block, which has saved the data in external memory, simply informs an Ethernet transmit manager that does the load balancing. It tells the appropriate transmit block, hey, you have a packet that needs to be sent. The transmit block reads the packet from memory, pushes it into the vertical column to be sent, and that's that. It's pretty simple. In the case of encryption, instead of the transmit manager telling the TX block to fetch the data and send it, it could instead tell an encrypt block to fetch the data, encrypt it, and then forward it within the column to the appropriate transmit block. Now, to receive data from PCI Express to send it out the Ethernet interface, the PCI Express can write it to memory, tell the transmit manager that, hey, here's some more packets that need to be sent. It tells the transmit blocks independently, and they can just fetch the data and away you go. Now, all through this example, I'm assuming that the packet data goes to external memory before it's forwarded. Really, that's not necessary. If your application is a low latency application, you can take the data, forward it directly from the receive block to the appropriate transmit block, do whatever buffering you need to do in the FPGA logic itself, and you have a much lower latency implementation of a switch or a SmartNIC. So with this way of using the network, it provides you with a lot of flexibility as to how data moves throughout the system and where it goes. Once the packet is ready to go, each individual transmit manager is informed. The packet then is read from memory and sent. Okay, finally, let's discuss our third application, storage acceleration. So the design goals for this application are to accept data from the host, send it to multiple compute engines that live inside the FPGA, operate on the data, and forward it to a storage array, where this might be over NVMe, which is based on PCI Express, or it might be over RDMA or RoCE, which is over Ethernet. In the other direction, we need to accept the response data from the storage array, operate it on in the opposite direction, and then forward it to the host. So this looks pretty similar to our previous designs. The host is able to write directly to the compute engines in the host to NVMe direction. All it does is issue a transaction to the correct address, the NOC forwards it, the compute engine does its work, and in the case of NVMe, simply writes to the PCI Express core, that's the second one, and this is transferred as NVMe to the eventual storage. If you were using Ethernet for RDMA or RoCE instead of NVMe, then it would be really the picture that we looked at previously with the SmartNIC. It would go to the transmit engine, that would fetch the data, and away you go. In the return path, the data coming from the NVMe interface is written into the compute engine, and then the compute engine in turn writes to the appropriate address that causes the data to be sent up to the host. And that's the entire application. In all of these cases, you've seen that the communications infrastructure used a minimum of FPGA logic, and we were able to use all of that available FPGA logic for the actual compute. So this brings me to my summary. Having a NOC built into the core of the FPGA makes design verification and timing closure significantly faster and easier. And the way we've implemented it can be used for AXI transactions, for packets, and for arbitrary streams of data. We have many network access points throughout the FPGA core. In the specific example of the 7T1500, we have 160 different network access points. As we've seen, the hard IP interfaces can communicate with each other without requiring the FPGA core, such as the example of the PCI Express interface populating GDDR6 memory. And we have hardened support, such as our packet mode, to make 400 gigabit per second Ethernet easy to implement. So the new Speedster 7T FPGAs with 2D NOC support more than 20 terabits per second of on-die throughput throughout the NOC, 32 lanes of 112 gigabit per second SerDes that we can use to implement for 400 gig Ethernet max. We also have PCI Express Gen5 by 16 and a second PCI Express Gen5 by 8 hard controllers. And we have GDDR6 for low-cost, high-bandwidth memory at 4 terabits per second. So with that, I'd like to say thank you to everybody for listening, and back to you, Dan.
Thank you for all participating in the SemiWiki webinar series, and have a good day.